Thank you very much. Welcome, everybody. As probably most of you know, the human brain is an astonishingly complex system, which comprises billions and billions of neurons that form a network of interconnected neuronal populations. And that makes it apparent that if we want to understand the functional organization of the human brain, functional integration or brain connectivity is key to understand that. And that is not only true for the healthy human brain, but also for psychiatric or neurological disorders, where we know that alterations in the functional connectivity are a hallmark of most of those diseases. And we see it throughout the conference that the concepts of functional integration and brain connectivity is very important. Fields like connectomics or network neuroscience are really flourishing and have provided deep insights into the human brain. But there are also some challenges, and one of the challenges is that the measures that we typically use in connectomics, for instance, are like structural connectivity or functional connectivity. Those measures are usually undirected. And that is in contrast to what we know about the human brain, for instance, in terms of cortical hierarchies, where we know that there is differences, functional differences, in forward and backward connections. So what we would want to have is a measure or a model of directed or effective connectivity. And one way to do that, and it has already been mentioned in the previous talk, is dynamic causal modeling. And that has been applied quite successfully in the field, but as again has been pointed out already, it's usually very restricted in the sense that it rests on very specific hypotheses, and even more importantly, it's usually restricted to small networks that comprise maybe 8 or 10 regions. And the reason for that is that if you go beyond that, it just isn't computationally feasible anymore to invert the models. Now, that's not always an issue, but if you're looking at very distributed networks and activations, or if you're more interested in a rather exploratory approach, then the limited size of the networks becomes an issue. And what you would like to have in a situation like that is a model that can infer effective connectivity at the whole brain level, potentially including hundreds of nodes. And we have recently introduced a method that is called regression DCM, which is basically a novel variant and simplification of classical DCMs that tries to move in that direction. And I want to give you a very quick hint, without going into too much details, of how this model works. So we start with a classical default implementation of a linear DCM, which has the A matrix, the endogenous connectivity, which reflects the directed connections between brain regions, and the driving inputs, which are encoded by the C matrix, which is how experimental manipulations from the outside can perturb the system. We now take this linear DCM from the time domain and bring it into the frequency domain using the Fourier transformation. And under additional simplifying assumptions and modifications of the model, and by using suitable priors, we basically end up on the right side with a Bayesian linear regression-like model in the frequency domain. And the nice thing about a Bayesian linear regression model is that you can solve them very, very efficiently. And that allows us to potentially scale up the networks to very large sizes. We have recently also introduced sparsity constraints to the framework, where you now can basically start from a fully connected network and then prune this network to the most relevant connections given the data that you have. Now, we have done a lot of simulations and tests to demonstrate the phase validity, but I'm not going to show you those results, but show you some first empirical proof of concepts that the method actually provides sensible results, I think. And the first point, or the first data set that we applied the method to, was a simple hand movement paradigm that was recorded with FMRI, where subjects either had to perform left-hand movements or right-hand movements synchronized with the blinking of a visual cue. And in total, we had 25 subjects that participated in that study. And what you can see then is the typical bold activation patterns, typically see activation in the primary motor cortex, supplementary motor areas, as well as somatosensory cortex. So this is very classical. And we then use the Brainotome Atlas as a whole brain parcellation scheme to basically extract for each and every subject from each of those parcels the bold signal time series. So that means that we are left with a DCM that has 208 regions. And in the first step, we then used the structural connectome that is also provided by the Brainotome Atlas to inform our A matrix, so the endogenous connectivity matrix of the DCMs, in order to then estimate the parameter values or the strength of all of those connections. And as you can see at the bottom, this left us with roughly 18,000 parameters that had to be estimated. And when we do that, we get a pattern, an average pattern that looks like this. And I just want to go through it very quickly to show that there is some plausible structure in what you can see there. So first, we see that there are very strong driving inputs and functional integration among the regions that are highlighted here. And those are mainly motor regions in the precentral gyrus or in the postcentral gyrus, SMA, but also visual regions, which is consistent with the blinking of the visual cue. But of course, there's also other structures. So for instance, there's also integration among those modules that I was just highlighting, as well as these very prominent peaks, which represent frontal regions and parietal regions, which is then more in line with the idea of the cognitive aspects or the executive control aspects of the task. But we went one step further. We also looked at the differential contrast between left-hand movements and right-hand movements. And when we do that, we get a pattern that looks like this. So those are the same results, just presented as a connectome and projected onto the 3D whole brain volume. And what you can see is in green, connections that were significantly stronger during left-hand movements as compared to right-hand movements, and the opposite for the red arrows or lines, those were significantly stronger during right-hand movements as compared to left-hand movements. And that's multiple comparison corrected across all those 18,000 connections. And what you can see is this very beautiful and expected contralateral pattern where connections in the contralateral hemisphere are more pronounced, and it's exactly between those motor-related regions that you would expect. So the supplementary motor area at the top, then on the rightish side, the primary motor cortex, and at the bottom, it's the somatosensory cortex. So that's very nice. And what is also nice is that we can get those results not only if we assume, as I've done now, a fixed A matrix or a fixed connectivity structure using structural information, but also when we start from this fully connected network and then prune the network using sparsity constraints. We get very similar results then. And this is an arguably even more challenging situation because then we have more than 40,000 parameters. Good. In the last 2 minutes or so, I want to very quickly give you a hint or a teaser of how this model can also be applied to clinical data sets and how it might be helpful in a clinical study. So here we use data from the BSNP study, which is a very large data set from the United States, which comprises psychotic patients, and here we have different subgroups, schizophrenic patients, bipolar patients, and schizoaffective disorder patients. We have matched healthy controls and matched first-degree relatives. And those subjects all performed a resting state experiment, and then we used the data to fit our whole brain models. And then started to look into group differences between both the patients and the healthy controls, as well as the subgroups. And the first thing that we can see is if we look at patients, first-degree relatives, and healthy controls, is kind of a progressive alteration of the connectivity patterns from disease or from health to disease. So as you can see on the left, patients were more different from healthy controls than they were from first-degree relatives, and those two relatives and healthy controls didn't differ very much. And this is, again, multiple comparison corrected across all the connections that we have. It's the same parcellation scheme, so again, it's more than 40,000 tests. And we can also start to look into differences between the individual subgroups and also find some differences between those groups. And I don't want to stress those results too much because it's very preliminary and we still have to look into this more closely, but it should give you a hint of how you can use the model also in the clinical setting. And with that, let me put up my summary slide and just point out that if you are interested in that method, it's openly available as part of this tapas toolbox that our unit provides. So if you're interested, check it out, and you can always come back to me if you have questions. And with that, I'd like to thank all my collaborators, in particular Klaas, who's my supervisor, and of course you for your attention. Thank you.